Assalamu alaikum wa rahmatullahi wa barakatuhu. So today is our lecture number 11, probability methods in engineering. So in the last lecture we have seen the counting methods of the all possible outcomes of a sample space. So in that we have seen k permutations and k combinations and also the sampling without replacement. Today we will be looking at the sampling with replacement. So sampling with replacement means that whatever we have the collection of objects, so we will take that sample from that collection of objects and we will note it down and we will put it back into the collection of objects, and again if we have to repeat it, we will repeat from the whole collection of objects instead of reduced number of collection of objects as we have seen with the replacement sampling without replacement. So consider a selection, consider selection of an object, an object from collection of objects replacing the selected object and repeating the process several times. So each time replacing the selected object before making another selection. So this is actually called the sampling with replacement. So each selection is the procedure of a sub-experiment. So the sub-experiments are referred to as independent trials. So why they are independent trials? Because there are two things in it. The first one, that we can actually select the same object again, and the other reason is that because we are putting the object back into the collection of objects, so whatever we have selected for the experiment. So to understand this, let's look at the problem. So I will paste it from the book. So in this example it says that there are 4 coins in the deck that we have seen previously in the last lecture, deck of 52 cards. You are given 7 cards at random from the deck. After receiving each card, you return it to the deck and receive another card at random. So observe whether you have not received any queens among the 7 cards you were given. What is the probability that you have received no queens? So now this is the same problem, but in this scenario we have to put back the card and we just have to see if we have received the queen or not. So in this example it would be very simple, because sample space would be simply 52 power 7 possible outcomes it will have, and the probability there are, means for no queens, for no queens there will be 48 power 7 outcomes. So it simply means that we have every time we have 48 cards, means leaving behind the 4 queens of that deck of 52 cards. So we have to see what is the probability for so the probability of having no queens will be simply 48 over 52 power 7. So that comes out to be 0.5710. This can also be seen with the tree diagram, as we done for in the previous lecture. So obviously it will start with root, and the first branch, first card, if it is queen, so our probability will be 4 over 52, and probability of getting no queen in the first card will be 48 over 52. So if there is no queen, so we will get another card Q2, and probability again will be, now because we are replacing the card, so we have again 52 cards to select from. So similarly no queen card will be again 48 over 52. So this will be proceeded same way up till Q7. So its probability will be 452, 4 by 52, and N7 its probability will be the same as 48 over 52. So the probability of having no queen in the 7 cards will be 48 over 52 into 48 over 52 up to 48 over 52, which is 48 over 52 power 7, which is the same we have seen. So this will be the same probability. So here we can see that this is a bit easier to understand, that if we replace the object while we are doing the sampling. Now let's look at this theorem. It is 2.4. So it says that M distinguishable objects there are m power n ways to choose with replacement and ordered sample of n objects. So very simple example to understand is if we have the binary number of 10 bits. So this is example actually 2.13. So it says that we have binary number of 10 bits. So how many possible combination can be made? 2 power 10, because we have the ordered also, and we have 10 and we are replacing 1 and 0 because binary number has only two basic elements, 1 and 0. So we will select either 1 or 0 10 times, and obviously we have to replace it back, so otherwise it's not possible. So it will be 1024 binary sequences. So similarly the letters, this is another example, 2.14. it says that the letters A through Z, letters A through Z, so can produce 26 power 4, which is 4 5 6 9 7 6 4 letter words. So okay, so let's see this another theorem, 2.6. it says that the number of observation sequences for n sub experiments with sample space S is equal to 0 1, with 0 appearing n naught times and 1 appearing n1 times, which is actually equal to n minus n naught times, is n choose n1. So here remember that this 0 1 is not only the binary numbers. Here 0 could be 0, we can relate it to say failure of some experiment, and 1 we can call it as the success. So maybe we are checking when we are manufacturing an ICs and we are testing them. So we are testing a batch of 10 ICs, so we can say that if 10 ICs, which one of them is a failure and which one of them is success. So we can use these 0 1 to represent that also the thing. So repetition of that sub experiments. So 0 1 here is not only for the binary numbers, although binary numbers can be used for them too. So this theorem can be, this theorem means theorem 2.6 can be generalized to sub experiments with m is greater than 2 elements. Means sample space here we have just like 0 1, it can have more than 2 elements in sample space. So for n trials of a sub experiment with sample space S sub is equal to S naught up to Sm minus 1. So we want to find, so what we do, we want to find the number of outcomes in which and S naught appears n naught times, S1 appears n1 times, and so on. So S2 appears n2 times, and so on. So this is only possible if n naught plus up to n m minus 1, they will count up to the n. So the notation for that would be n choose n naught comma n1 comma so on up to n m minus 1, and which can be written as n factorial divided by n naught factorial, n1 factorial, so on up to n m minus 1 factorial. So this is actually known as the multinomial coefficient, while the theorem 2.6 is actually binomial coefficient that you might have seen in your mathematics courses somewhere. So it is known as the multinomial coefficients. So this is actually defined in the book as theorem 2.7. So we can write the definition for this multinomial coefficient as for we have written for the binomial coefficient in the last lecture. So multinomial coefficient, so it says that for an integer n which is greater than or equal to 0, we define n choose n naught comma up to n m minus 1, which is equal to n factorial divided by n naught factorial, n1 factorial up to n m minus 1 factorial for n naught plus up to plus n m minus 1, which is equal to n, and ni belongs to 0 1 up to n, and I is equal to 0 1 up to m minus 1, and it is again 0 otherwise. So 0 otherwise means that other than these values we cannot calculate these numbers. So that's what we have explained in the previous lecture. Okay, so let's see an example. Again, I will copy it from the book and will paste it here. So it is quiz 2.2. It says that consider a binary code with 4 bits in each code word. An example of code word is 0110. So obviously here we have S with 0 1. So it says that how many 4 bits words we can have. So A part says that how many different code words are there. So the different code words will be 2 into 2 into 2 into 2, which is 2 power 4 m power n, so which is equal to 16. So we will have the 16 different code words having 4 bits. So because they are simple, we can even write them here very easily. So starting with 0 0 0 0 0 0 1 0 0 1 0 0 0 1 1, and So 0 0 1 1 0 1 0 0 0 1 0 1 0 1 1 0 0 1 1 1 1 0 0 0 1 0 0 1 1 0 1 1 0 1 0 1 0 1 1 1 1 0 0 1 1 0 1 1 1 1 0 and 1 1 1 1. So I think so I have not missed anyone. So 1 2 3 4 5 6 7 8 9 10 11 12 13 14 15 16. So yes, we have written all of them. So the next part says that how many code words have exactly 2 zeros. So exactly 2 zeros, we will be having this one, this one, this one, this one, this one, this one. That's all. So we will have these 6 numbers which will be having exactly 2 zeros. So in other words, we can find out by using 4 choose 2. So 4 choose 2 is actually n4 factorial divided by 2 factorial into 4 minus 2 factorial. So this will be 4 into 3 into 2 factorial divided by, so it is 2 into 1 into 2 factorial. So this is 12 by 2, which is 6. So we will have the 6 elements as we can have seen from the above samples. So they would be, we can write it because we have figured them out. 0 0 1 1 0 1 0 1 0 1 1 0 1 0 0 1 1 0 1 0 and 1 1 0 0. The next part says that C, which says that how many code words begin with 0. How many code words begin with 0? So how many code words begin with the 0? So it means that the first bit must be 0. So first bit has the option that it will be it would not be repeated twice, but rest of the bits, 4-bit words, rest of the bits will be either 0 or 1. Third bit could also be 0 or 1, and this is, so there is there are we can see here there are options of we have the 8 ways of choosing code word that starts with 0. So that's also can be seen from here. So these are 1 2 3 4 5 6 7 and 8. So these are 8 possible ways to select the code words that start with 0. And the D part says that in constant binary ratio, each code word has n bits. In every word, m of the n bits are 1 and the other n minus m bits are 0. How many different code words are there in the code with n is equal to 8 and m is equal to 3? So this is a very simple problem. So that we have n is equal to 8 and m is equal to 3. So for that we could have 8 choose 3. So it would be 8 factorial divided by 3 factorial, 8 minus 3 factorial. So it will be 8 into 7 into 6 into 5 factorial divided by 3 into 2 into 1 into 5 factorial. So this will be cancelled out. So this will be cancelled out here. So this will be, so we will have the 56 code words for this scenario. So I hope you have understood. So I hope you have understood all these problems. So we will stop here and we will continue with the next topic in next lecture. Stay blessed. Assalamu alaikum wa rahmatullahi wa barakatuhu.